Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2019, problem number 1. Let G be a finite group and let f be a function from G into itself, satisfying the following condition: f of x, y, z equals f of x, f of y, f of z for all elements x, y, and z of our group. We wish to do two things. For part A, prove that if the order of G is odd, then this function right here is an endomorphism. So in other words, what is an endomorphism? It's a function from G into itself, which takes the neutral element of G to itself, so f of 1 should be equal 1, and moreover, f of xy should be equal f of x times f of y. And part B, is the same true if the order of G is assumed to be even? Maybe it is, maybe it isn't. So here are my hints for this problem. First, recall this notion of the order of element. If small lowercase g is an element of group G, then we define the order of element to be the minimum over all positive integers k, such that g to the power of k equals 1. So it's the least exponent, in other words. And this crucial fact, for any element G, the order of element G divides the cardinality of the whole group. Always, it's always the case. And after realizing that, just set x, y, and z to be 1 and try to find the order of f of 1. And for part B, just consider z2 with addition. So set consists of elements 0 and 1. And addition, yes, add addition modulo 2, and define function f of x which equals 1 minus x, and consider what happens for this function. So give this problem a try. Right. So yes, for part A, let's take set x, y, and z to be 1. 1 means the neutral element of our group. What do we have? F of 1, 1, 1 equals f of 1, f of 1, f of 1. Very nice. But on the left hand side we have f of 1, on the right hand side we have f of 1 to the third power. Alright, since this is true, I can invert f of 1 on both sides. I can multiply on both sides by f of 1 inverse, because we are dealing with groups and every element has its inverse. And what do we have? Well, on the left hand side we have 1. On the right hand side we have f of 1 squared. Perfect. Which means that the order of 1, f of 1, is either 0 or 1. Order of f of 1 is 1, sorry, not 0 or 1, but 1 or 2. 1 or 2. Well, but notice that since the cardinality of G is odd, and since, well-known fact, the order of any element is a divisor of the whole cardinality of the whole group, it cannot be 2, because 2 does not divide any odd number. We must have f of 1 equals 1, or order of f of 1 equals 1. Which of course means, i.e., f of 1 equals 1. Very well. F of 1 equals 1, so the first condition for being a morphism of a group is satisfied. And notice that I will take once again my equation and I will set z to be 1. Then we have the following: f of x, y, 1 equals f of x, f of y. f of 1, but f of 1 as we know it is 1. Which means that both conditions for being a group homomorphism is satisfied. Which means that f is an endomorphism. Which closes the proof of part A. Notice that we have used in a substantial way the fact that the order of our group is odd. So this should suggest that maybe for even cardinality of G, probably the result is no longer true. And to convince yourself, let's consider this example. Exempli gratia. So let G be Z2 with addition. Z2 with addition, probably the simplest non-trivial group. Well, and what about our function? And I will define my function f of x to be 1 minus x. So it takes 0 to 1 and 1 to 0. Where clearly f is not an endomorphism. Clearly, f is not an endomorphism. Why? Because f of 0 is 1 and not 0. And it should be 0. Alright, but does this function satisfy our condition, namely f of x, y, z equals f of x, f of y, f of z? Well, let's verify it. We have only 4 cases to verify. Notice our group is commutative, so we have only 4 cases. First, f of 0 plus 0 plus 0. Well, what is that? Well, it's f of 0, and f of 0 is 1. And what about f of 0 plus f of 0 plus f of 0? Well, it's 1 plus 1 plus 1. So it's 1. Yes, because we are dealing with group Z2, modulo 2. We are doing addition modulo 2. Alright, second case, 0, 0, 1. It's f of 1. F of 1 is 0. F of 0 plus f of 0 plus f of 1 is what? It's 1 plus 1 plus 0. It's 0. Again, well and good. Next case is f of 0 plus 1 plus 1. It's f of 0 again, because 1 plus 1 is 0. So it's 1. F of 0 plus f of 1 plus f of 1. What is that? It's 1 plus 0 plus 0. So it's 1. And finally, f of 1 plus 1 plus 1. It's f of 1. And it's 0. While f of 1 plus f of 1 plus f of 1. It's 0 plus 0 plus 0. 0. So our function f satisfies the condition given, but it is not an endomorphism. So the answer for part B, no, the claim is no longer true if the order of G is assumed to be even. And that closes our problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.